Hello, students. So I think we had some challenges in the uh, live streaming that we had scheduled. So that's why we started this one. And I guess we'll just wait for a few seconds as we had few students on the other chat, and they may come back here, right? So yeah. So I think and now we are getting folks here. So okay, just give me a moment. Perfect. So, thank you, students. And then finally, we are able to, start. Hey, Monish, thanks, man, for joining. Yeah, and we will just get started. Okay, fair enough. So, I think, good evening, Rosni. We'll just wait a second or two for for Mahesh. Mahesh, are you on? Okay, great. Perfect. So I think let's get going with our today's topic, and that is obviously very important. That's a very important topic of electrostatics, right? So in our previous lectures so far on electrostatics, we have understood, right, what is charge, right? Charge, and we have understood that charge is that property of matter which defines, right? So it's a property of matter or that property of matter which defines degree of electrification, right? So this was the first definition that we understood as we came into electrostatics, and we have already understood that. I will not go too much into it, but let me establish the connection of the dots so that you understand, what the things which we are discussing, the whys behind that, right? So yeah, so this is what charge is, right? And then to understand the degree of electrification, the first thing that we understood was something called as Coulomb's law, right? And in Coulomb's law, we understood that if two point charges, Q1, and remember the word point charges, if two point charges Q1 and Q2 are separated by a distance R, and assuming both are like charges, I'm assuming that both are like charges, then and if unlike, it will be attractive, but magnitude would remain the same. So the force of the electric force executed by one charge on the other, right? So say if F12 is the charge experienced by the charge exerted by Q1 on Q2, obviously as they are like charges, it will be repulsive in nature. And this F12 in Coulomb's law was defined as 1 by 4 pi epsilon naught product of magnitude of both the charges by the square of the distance, right? So, which is why this is also called as your inverse square law, and where epsilon naught is nothing but your permittivity of free space, right? So we have understood these points, right? And and after that, we have understood that okay, once we understand the force between two charges, we defined three quantities. One was called electric field, second one was potential energy and potential, and third one were your lines of forces, right? Your lines of forces. And using these three concepts, we have defined force per unit charge. We have defined potential energy as, or potential as, your work done upon unit charge minus, and obviously U or potential energy is just the minus of work done, right? And similarly, lines of forces, we have understood that visually, if we represent the electric field, so these are the three different physical quantities using which we try to explain something called as electric field, right? And we have also understood that what does this word field mean in physics, right? So we know that the word physics is the word field in physics is not only related to or confined to electricity. So in my last lecture, I have explained that whenever we talk about exerting a force, right? So we know that force is nothing but in layman's term, it's a pull or a push. Okay, so I have a water bottle. If I want to apply a force on this, I can either push it or I can pull it. So obviously, I can push it or I can pull it. Now, the common thing that I'm doing here is both in push or pull, my hand is in contact with it, right? Now, but in case of things like, we say that Earth revolves around the sun due to gravitational pull, right? And we say that if something is placed relatively close to Earth's surface, Earth will pull it. Or we know that some kind of materials, right? So just give me a moment, students. So getting something. Okay, fair enough. Yeah. So yeah. So in those cases where force force is experienced not by contact but from a distance. I repeat, in physics, wherever you would see force is experienced from a distance and not by contact, in that scenario, the force is always explained by a term called field. Okay, I repeat, in physics, when force experienced by one particle from the other is is not due to contact, it is always explained by something called as field. So we have studied about gravitational field. Here we'll study about electric field, and in different and some in a different chapter we'll study about the magnetic field. So these are the three dominant field which we taught in physics, right? So yeah, but still there would be a lot of similarities between them. Okay, now in the as per Coulomb's law, right? As per Coulomb's law, we have understood that, say, here is a charge Q1, okay, and then at a distance r, there's another charge Q2, assuming both are positive charges or like charges by nature, okay, and if the distance is r, so obviously we know force is 1 by 4 pi epsilon naught Q1, Q2 by R squared. I'm just talking about the magnitude, okay? So magnitude would be this much, right? F1 choose magnitude, okay? So which means your electric field intensities, your modulus or magnitude would be force per unit charge. So if I want to find out the electric field at point Q2, or sorry, this is point A, this is point B. If I want to find out electric field at point B, then only this charge Q1 is giving a force F12. So obviously in the same direction, we'll have this one will experience electric field, and I can try to say it E12, right? So the E12 would be force per unit charge, so which is nothing but into 1 by Q2. So obviously Q2 cancels out, and this becomes FQ1 Q2 FQ1 by R squared, FQ by R squared, right? So this is how we have studied about the electric field at a point due to another point charge. Now the interesting thing is, right, now assume that we bring another charged particle, okay, suppose Q3 here. Okay, now we are going step by step. Okay, students. So first we studied electric field due to 2 point charges. Now we are studying something called as due to discrete charge distribution. And this background is needed to understand continuous charge distribution. Okay, so suppose there is another point called C, and where we have a charge Q3. Obviously Q3 will exert a force, your F due to 3 on 2, So obviously there will also be an electric field due to 3 onto in that direction, right? And assume these distances are 2. So I can say that is the electric field due to charge Q3 at point B. Now, if I ask what is the net electric field, so obviously it would be the vector sum of VE12 and E32 resultant, right? So resultant, and obviously because electric field is a vector, so we need to do vector addition. We cannot just do scalar addition like your 2 coulomb plus 3 coulomb equals to 5 coulomb. It will depend on the angle theta between them. Now, suppose we have a point, suppose D here, and a point, say E here. Okay. So similarly, this would also execute a field. So I can say E due to 4 on 2. This one will also execute a force, and it will be due to an electric field E due to 5 on 2. Now, I have got so many vectors, and obviously in that scenario, I can say this is nothing but the summation of all the electric field intensities, right? Where I goes from 1 to n, if there are n number of particles, right? So, so this is what is called, say at different point, if different charge particles are there, then we can find it like this. Okay. Now let us move one more step forward. Okay, and let us go to something called as something called as continuous charge distribution. Okay, and for that, now let me give this scenario. Okay, so let us take a new scenario, say 1. Okay, and in this scenario, let us consider I have a rod of length L. Okay, and this is a conductor. So I'm saying it's a metal. Okay, and this width is very small. If this width is very small, I can assume that it's just like a thin long wire. Okay, so and in this situation, suppose there is a point P here. Okay, which is, say, okay, I'll put it right here. Okay, point P. So which is at a distance, say R, on the axis of this uniformly charged rod. So I'm saying I have taken a uniformly charged conductor conducting rod, and I have given it a charge Q, which will be uniformly distributed over the surface of this conductor. And at a distance r from it on its axis, I want to find out what is the value of the total electric field. Now, the question is, let us think, can I apply Coulomb's law directly here? So I know total charge here, and this charge is, say, even if it is q, we know that in a denominator that will get cancelled out because electric field is force per unit charge. We know the total distance, right? Now, can I apply Coulomb's law, or Coulomb's law to finding out the total electric field intensity here? Can students just type their answer quickly on the chat box? What do you think? I just give you a minute. So please type down your answer. So I repeat my question. Can I apply Coulomb's law because I know total charge, right? I know the length or the distance, right? And value of 1 by 4 pi epsilon naught. This is a universal constant, right? So 8.85 into 10 to the power, or we can say roughly 9 into 10 to the power 9 Newton meter square per Coulomb square. So we already know this. Okay. So when we know all these three things, can I directly put E here is 1 by 4 pi epsilon naught q by distance is L plus R squared. Is it right or wrong? So students, just think through it and type down your answer in the chat box. Uh, don't worry whether you go right or wrong. I would encourage you to type your answer in the chat box, and then we would see why that is right or wrong, or we'll go to next step. Wrong, wrong. Very good. Very good. That's it. So it is wrong. And the reason it is wrong is first point is Coulomb's law is defined for point charges. Okay. And why point charges? Just imagine students, this end of the rod is at a distance L r from here. This end of the rod is at a distance L plus r from here. This center would obviously be at a distance L by 2 plus R. This place will be at a different distance. So when my distance is varying so hugely, I repeat, when the distance is, when there is such a huge variance in distance, when the distance, when there is such a huge variance in distance, I cannot apply Coulomb's law directly, and obviously thereby I cannot find out force between those two charges, and obviously which also means that I cannot find the net electric field, right? So we need to find out an alternate, okay, and we need to see how to solve it, okay, and that is the background of continuous charge distribution. And as I said, what are the problems? I'm noting it down here. If you want, you can note down. So the reasons why I can't apply Coulomb's law directly directly to find electric field intensity E, right? First thing is Coulomb's law is defined only for point charges, right? It is defined only for point charges. And obviously the reason for that is distance distance varies a lot in this scenario. Okay. See, because obviously 1 by 4 pi epsilon naught is constant, q by r square. So charge we have made it at only a constant, it is total. But as this part is hugely varying, so that is why I cannot apply Coulomb's law. Remember, students, knowing this is very important because I always encourage that let us understand the problem. If we understand the problem properly, I think finding the solution is half done. Okay, because without understanding the problem, if we try finding out solutions, we'll end up getting wrong solutions. Okay, now in our next few minutes, whatever we'll study, we would see how do we eradicate these problems. I repeat, in throughout our next few deductions which we'll do, we would see how we will nullify this problem and this problem so that I can apply Coulomb's law directly. Okay, that is the key. If someone has understood what I have said in last few minutes, trust me, students, apart from the complications of integrations of mathematics, it would be a cakewalk for you. If anyone wants me to repeat anything, ping it in the chat box. I can repeat, or else I would go forward. I'll pause for a few seconds here. Yes, mice. We'll do DL. We will see, and we will do integration. But the reason why we discussed all this is let us understand the why behind that. Okay. So looks like I think all the students have understood what I said in last few minutes, and obviously now let us move to the next step. Okay. Now, in this scenario, in this scenario, in this scenario, now my job is to find out a small interval, find out a small interval such that in that interval I can say distance as constant. Okay, and for that I would use this concept. So say from this point P, let us take this point, okay, which is at a distance, I can say, suppose, okay, this point, which is at a distance, nothing but x from point P, okay. The distance of this point, let me say this one as your, what do you say, let's say this is x, so, okay, or x we have already used, right? So say, let's say this is m, okay. Now let us take a very small, this, interval here, and let this distance be called as dl or dx, okay. So I repeat, if I can put a magnifying glass here, what I have done is at a distance x from the point, I have taken a small interval called dx, okay, such that dx tends to 0. See, this is tends to 0, just like you study in your calculus, okay. So your delta x tends to 0, okay. If it tends to 0, can I say that this distance, if it is x, this distance is nothing but x plus dx, this end part, and can I say x equals to x plus dx as dx is very very small, or as dx tends to 0, we can say this, right? So this solves our basic problem of making the distance constant, and using this interval now we can find out coulombic force, and force per unit charge will give us the total field intensity. Okay, now if we move further, and there is one more reason why we have selected this as an interval. Now suppose someone says that, no sir, I don't want to select this as an interval, rather I want to select this as my interval, right? So this is also, very thin, so someone can think I can use this also as my interval. So if someone chooses this as an interval, will this be right or wrong? Can you students type down in the chat box? I repeat, if someone chooses this new interval, is it a right approach or wrong approach? Please type down your answer in the chat box. Okay, so this would be wrong for the fact that, see, our initial problem was distance was having a huge variance, and if I select this interval, still that problem exists, right? So I have not solved anything, and that is why initially I was saying that let us understand what why we cannot apply Coulomb's law, because once we understand that, other parts is a cakewalk. Okay, so that is why you cannot use this as an interval to solve this problem. So the right one would be say, yeah, like what we defined initially. Okay, so let us now go ahead and solve it. And another reason why we should be selecting this is when I when I integrate this interval from lower limit to upper limit, it completes the entire body, or it completes the entire object for which I want to find out the total electric field intensity. Okay, so A, in this interval, distance does not vary too much, right? And second, when I integrate from lower to upper limit, it covers the entire body. These are the two very important points based on which we select an interval. Okay. So now, if you have understood how we have selected this interval, the rest part is very easy. Okay. So rest part is, if total charge is Q and this length is L, can I say that charge per unit length will be Q by L, right? If charge per unit length is Q by L, then charge in interval dx will be how much? It will be nothing but Q by L into dx, right? If charge in this interval is Q by x dx, then what would be my what would be my, okay, I'll just rewrite it here. Q by L dx. If this is the charge on this interval, what would be my electric field intensity? 1 by 4 pi epsilon naught. Okay, or dE, small intensity electric field intensity, E would be 1 by 4 pi epsilon naught Q by distance square. What is the distance? R plus L. R plus L square, correct? So this would be my dE. If this is dE, can I say that E is nothing but the integration of this, and where the limits are, what is the lowest limit of your or what is the lowest value of your x? That is nothing but r, where your interval is here. At that time the distance is r. So from r to what is the highest distance when it is here? That is r plus L. Now all that we need to do is to solve this integration problem of mathematics. Okay, so now let me erase it because we need white space for solving it. Okay, and we know that we can take out the things which are constant out of the integration sign, right? So as I can erase it on the board, let me start using that facility. Okay, so what I would do, I can take 1 by 4 pi epsilon naught Q by L, all these, and R plus L square. All these are constants, right? So I can take all of them out of my integration. So which would mean that my integration would be just dx from R to R plus L, right? And we already have studied in integration that integration of x to the power n dx is nothing but x to the power n plus 1 by n plus 1 plus c. Because it is definite integral, we need not have the constant. We can just put lower limit, and here we can put the upper limit, right? So we'll just use that funda here. Okay. Now so which would mean q by 4 pi epsilon naught L into R plus L squared x going from R plus L to R, which is nothing but, I can say this is, if I put it here, right? So I can next write that is nothing but R plus L minus small r. So these two get cancelled out. So if these two get cancelled out, this L will get cancelled out with this L, and the answer would be q by 4 pi epsilon naught 1 by r plus L. Sorry, this is whole square. R plus L whole square, right? So this is your equation. Okay, so this will be the magnitude of the total electric field intensity due to the uniformly charged rod at an end of it. Okay, now let us move on to the next one. Okay, let's move on to scenario 2. Just give me a moment. I will just develop a bit of water. Now let us change the scenario slightly and see how to handle that one. Okay, So in this next scenario, scenario two, okay, what I would do, so say I would keep, I would keep the same uniform rod, total charge Q, total length L, right? And rather than on the axis, now let us try to find out on the perpendicular bisector. My drawing is not so great, so you need to compromise with that. So at a distance r on the perpendicular bisector, if it is perpendicular bisector, obviously this is L by 2 and this distance is also L by 2. Okay, in this scenario, at a point P, which is a distance r from a uniformly charged rod, what would be the net electric field intensity's magnitude? Let us try to find out. Okay, again, I repeat, we know we cannot. Okay, point number, let's go to step number one. Can I apply Coulomb's law? Can I apply Coulomb's law? The answer is no. For the fact that again the distance of this part will be this much, but the distance of this part will be this much, and distance of this part will be exactly r, and which varies a lot. So which means I cannot apply Coulomb's law. Now, obviously, in that problem only we have the solution. So we need to find out an interval such that first distance would not vary too much. B, when I integrate that interval from the lower limit to upper limit, it should cover the entire body. I repeat, these are the concepts based on which we select intervals. If you understand that, you can solve a lot of complex problems, which I would, kind of give you a hint towards the end of the class. Okay, so so now, again, I have two ways to select an interval here. If I select this interval, again, it would not work for the same reason we saw in the previous scenario. Because obviously, distance is not handled. So the distance is still varying hugely. There's a huge variance, which means I have not solved the fundamental problem which I wanted to solve. So this is not the right interval which I can take. A right interval that I should be taking would be something like this. So at a distance, say x from the center, suppose O is the center, at a distance x from the center, suppose I take an interval dx, okay, that will be the right thing. Why? I can say x equals to x plus dx as your dx is very very small or dx is tending to 0. So first problem, distance, that is resolved. Okay, or variance of distance is handled. Second thing, if I integrate it from here to here, it covers the entire body. So scenario 1 done, scenario 2 done. That means it's the right interval which I can use. Okay, now if this is the interval that I should use, now let us do just simple maths and see. Okay, if dq is the interval, okay, then what would be the force due to this segment on this? Let us try to find out. Okay, so I can first draw the force like this. If the force is like this, then obviously your electric field intensity would also be, your dE will be this one, right? This is the small electric field dE due to segment dx. Okay, if this is dE, let us assume this angle is theta. Can I say this is, if this is theta, obviously this angle will also be theta. So obviously this one will be dE cos theta, and this component would be dE sine theta. Again, you need not mug it up. I have explained that, in one of my previous lectures, how do we do vector component resolution. Okay, now if this is true, at a distance another x from here on the opposite side, right? at a distance x, if there is one more interval dx, will it also have an intensity called dE? If yes, dE, will that also have two components such that this one will be dE sine theta, this one will be dE cos theta, correct? And which means obviously, as these are vectors, right? So this sine theta component will cancel out this sine theta component, correct? And all we will have is nothing but your dE cos theta, correct? So all that we would have would be your dE cos theta, okay? So that is what we need to find out, okay? So that is why we can say that your dE magnitude is nothing but 1 by 4 pi epsilon naught total charge, that is q by total length L into dx kq by r square. Distance square is nothing but square of this thing, right? So I can say that this is nothing but r square plus x square root over, which means a square of this will be r square plus x square. Okay, so this is my total dE. If this is my dE, then this one would be my total electric field intensity E, correct? And if this is my total electric field intensity, now I need to put the lower and the upper limits, right? So it is so if this length is L, can I say that this is varying from minus L by 2 to plus L by 2, minus L by 2 to plus L by 2? Okay. Now, now rest rest is just a simple, your solution of integration. And as I said, I would, concentrate on explaining you the concepts, and I do not believe too much in spoon feeding. So I would leave you guys to solve this integration and find out what is the total field intensity, and you can send me up as an assignment. Okay? Any question? If someone could not understand, just ping me and I can repeat any part which my students want. Okay, I'll wait few seconds to see if anyone could not understand. I will repeat, or else we'll move forward. Okay, so I take a silence as everybody has understood this. Now let us move forward. And as I said earlier, hereafter I would start introducing more and more complexity with every scenario which we are going through. Okay, so the first two scenarios were very simple. Now let us try to get into a little more complexity. Okay, scenario. Let us go into scenario 3. That is so initially I said that it was a uniformly charged body, right? So this is suppose a non-uniformly charged metal rod. In that scenario, how we'll find it out? Let us try to understand that. Okay, so this is my metal rod of length L. I have given it a charge Q, but the difference is this is non-uniformly charged, which means, and suppose I want to find out the electric field here on the axis at a distance r from here. Okay, at a distance r from here, this is point P. Okay, now we very well know that we'll select something this as our interval at a distance x from the point, and obviously this is nothing but your dx. Okay, this part does not change. What I'm saying is here, as my charge is not uniformly distributed. Okay, I'm sorry. If it is a metallic rod, it will always be uniformly distributed. So say this is suppose it's a non-uniformly charged rod like this is. So that's the reason we have understood, right? That in case of a conductor, your charge distribution is an inverse function of the radius of curvature, right? So if radius of curvature, obviously for a rod would not change. So if radius of curvature is not changing, then it will always be uniformly distributed. So we need to take maybe an insulator, or we need to take a different material, maybe an amber or something, and see. Suppose we have given it charge q, such that if the relationship of charge distribution can be given as, suppose I'm saying that charge distribution is given as a function of length. Okay, so suppose it is given as a function of length or distance from the this point P. If it is given as a function of fx, which is, suppose I have given 3x squared plus 4x plus 5. If this is given, then we can apply our previous points to this and we can find it out. Charge distribution is given, so your dE would be nothing but your charge per unit length into length will be charge, right? So 3x squared plus 4x plus 5 dx. This is charge in that segment. Okay, so dE will be nothing but 1 by 4 pi epsilon naught, right? Charge q into other charges we don't need by distance. That is nothing but, in this scenario, this is x squared, okay? And then we need to integrate it. That is it. Okay, from the limits, what was the limit? The limit was from your uh, r to r plus l. Okay, now obviously you need to use your integration formula here, that your you can divide it into the smaller segments, right? So integration of 3x squared dx plus integration of 4x dx plus integration of 5 dx. You can put all the limits r plus l in all the scenarios, find out the integration by 1 by 4 pi epsilon naught. Whatever you get, that will be the answer. Okay, so this is complexity 1. Now now let me make it even a little more complex. Okay, let us go to scenario 4. If the charge distribution is not given as a function of x, because your we are integrating on an interval dx. Okay, suppose it is given as a function of u, f of u, right? Or maybe some other variable, a b c d, anything but not x, right? So if it is given as, suppose au plus suppose a1u plus a2u square plus something, right? In that scenario, if you integrate with dx, right, what you need to do is convert this u into x. So I repeat, in integration, once you will have f of u dx, you need to use the techniques of integration to express this function also in terms of as a function of x, because without which you cannot use the integral part of dx. Okay, so that is why those mathematical conversions will be there. And remember, students, if we keep complicating it further and further, you can establish any model of any kind of body. Okay. Now, if we let me make it even a little more complex. Okay. So scenario five, if it's a non-uniformly charged body, okay, and if a mathematical equation can be found out for this, then you can measure that small interval dx, integrate it throughout the body, and you can find out. This could be done, but as this would need a very high degree of mathematics and very high degree of integration, that is not required, at least even up to your IIT course of IIT courses. Maybe obviously if somebody wants to be a physicist or a scientist, maybe you guys might end up doing some things much more complicated than this also, right? But then the concept remains the same, and that is why in my channel, as the name suggests, I believe in two things. A, making my students understand the concepts of physics, and I will help you apply those concepts to solve problems. But as I said, my core principle is I would not give you the spoon feeding of solving all the problems online. I would explain you a few things and then leave the rest for you to do practice. Okay, good, because you are not high school students anymore. Now let's move on to the next simple scenario. Okay, so this is just going like music, right? So in or maybe if you are going to a disc or a pub, right, you would first hear some slow songs, then maybe fast beat songs, then they would again change the beat. So that's how we are doing here also. We started with some very simple examples which you can do like this, like a point charge and couple of charges here and there. So if we solved it immediately, we increase the complexity a little bit. Now let us again see some one or two easier problems, so that you guys don't scratch your head too much. Okay, let's go into something else. Okay, and let us go into scenario six. Okay, scenario six. In scenario six, we have a charged ring. So we have a charged ring. Okay, so say I have a charged ring. Okay, please pardon my drawing students. So I have a charged ring, and I want to find out what would be the total electric field intensity at a distance x from its center on its axis, and which is the point P. I repeat, I have I'm taking a uniformly charged ring, and I want to find out the total electric field intensity E net at a point P on its axis, which is at a distance, x. Now let us see that. Okay. So the principles don't change. So let us go step by step. Okay, so that these steps would get registered in your mind. Okay, okay. First thing, can I apply Coulomb's law directly? Can I apply Coulomb's law directly? The answer is no. Okay. Now, if I cannot apply Coulomb's law directly, then what I need to do? I need to find out an interval such that a a the distance is constant, and b, if I integrate from lower limit to upper limit, it should cover the entire body. So for that, what I'm doing, I'm taking a small interval, say your dl on the periphery of this ring. So say for example, you have a ring, and you want to find out the electric field intensity there, right? So now let us go ahead and solve this problem. Okay, and we are saying that the total charge given is q. Okay, now if the total charge given is q, can I say that charge per unit length will be q by 2 pi r considering r as the radius of this, obviously ring, right? So if radius of this ring is r, so charge per unit length, this is nothing but my charge per unit length would be q by 2 pi r. Now charge per unit length is q pi r, so charge on this small segment would be into dl. Okay, so this would be nothing but my de. Now one again, the same interesting thing which we saw in our previous example. If this is if this is the charge segment dl, right, then obviously this will exert a force in this direction, which will be my de. And if this angle is theta, this angle is also theta, and which means I can say this is your de cos theta, and this one would be your de sine theta. Okay, de sine theta. Now I will have a similar segment on the other side also, right? So if I would have a similar segment on the other side, that would also exert an electric force in this direction, and obviously that one's cos component will be along this direction, sine component will be along this direction. Okay, so which means this component and this component will cancel out each other, and the net field would be only along that, your x-axis, right, or the axis of the ring. Now which means now the problem becomes very simple, and all that I need to do is I will just substitute those values here. Okay, so this is charge, and then obviously I need 1 by 4 pi epsilon naught. Okay, 1 by 4 pi epsilon naught, right, dl, and I need to find out cos theta. Now here is that problem I was trying to explain you when I said if it is a function of u, you cannot integrate it directly with dx, right? First, we need to convert it in terms of x, and then only you can use, right? So that is why I picked up this example immediately after that. Now, which means either I should have an interval called d theta, but theta would not change too much, because if you see it's a cone, and any place you see theta would not change, on that, right? So that is why I cannot integrate. All that now I have to do, I have to convert cos theta. So I have two options. One, convert cos theta, or your balancing convert. Let me say express cos theta as a function of your L, so that I can use the integral dl, or express cos theta such that it's a constant, right? Because if it's a constant, it will go out of the integration, and my integration will be very simple. Okay. Now, in this figure, if this is theta, can I say that cos theta is nothing but this is the base b by your hypotenuse h. Okay. Cos theta, I repeat, in a right angle triangle is always base by hypotenuse. So that is why if I put it like that, this problem will be solved. Okay. So let us do that. In place of cos theta, now I would say, okay, base, that is nothing but x x by, what is the value of this one? I can say x squared plus r squared, x squared plus r squared into dl integration. Okay, now let us see the limits of this integration. So limit would obviously be from, as I'm varying the length, the minimum length will be 0, and if I take it to 2 pi r, it will cover the entire ring, right? Now the interesting thing is, inside this integration, if you see x and x squared by r squared. Oh, sorry, I need to do a root over here. Sorry about that. Okay, this x square by r square root over. All these are in reality constant in this scenario because x is given, your r of the ring will not change. So obviously this entire part is constant. So in my trick which I said, right, that either we need to convert cos theta in terms of dl, or I need to express cos theta as a constant. I have chosen the second part, and I could express this part as a constant, which means I can take it out of the integration, which means my integration would be simplified like this: integration dl 0 to 2 pi r. So as we have discussed earlier, my job stops here. After this very simple integration, solve it, put the values, get the answer. As I have been saying, no spoon feeding, but I would help you understand the concepts step by step. And after that, I need you students to practice yourselves. Okay, I give you few seconds to ping in the chat box if you have a question. If not, we'll go to the next scenario. Okay. Now, let's go to the next scenario. Next scenario, as I said, yeah, I like to change the bits just like a DJ. Okay. Now, in the next scenario, let us increase the complexity a little bit. Okay. So, say next scenario would be scenario 7, and in scenario 7, what we will do is we would see. Okay. Suppose I had that initial rod, okay, and I suppose bend it to form, suppose a semicircular ring, okay. Excuse me for my drawing, okay. So say this is a semicircular ring, okay. Yeah, this is a semicircular ring, and this is center O. Okay, now I have bent, and this part is not closed. I just shown it just for sake of understanding. So I have bent that initial uniformly charged rod into a semicircular ring, and I want to find out the electric field intensity. So electric field intensity at the center of a semicircular uniformly charged ring. Okay, okay, and it might be appearing that this is simpler than the previous one, but there's an interesting trick here. So that's why I said this is a little slightly your different than or complex than the previous scenario. And again, the complexity is just how we want to module the integration to solve it. Apart from that, from physics concept perspective, all these are absolutely same. Okay, so let's get going. Total charge is Q. Obviously, charge per unit length will be Q by pi r because it's a semicircle. Rather than Q by 2 pi r, not be Q by pi r. Okay. Now, let us take an interval, dl. Okay. For understanding, say, let us take an interval dl somewhere here. Okay. Now, if I take an interval dl over there, okay, if I take an interval dl over there, let me say that this initial part of dl made an angle theta with the center of it, okay, and obviously now you will be able to understand that if I want to find out the electric field intensity here, I'm considering this as my interval. So this will be my distance. So going step by step. Step number one, for this entire thing, can I apply Coulomb's law directly? The answer is no. If I cannot apply Coulomb's law directly, next point is find out an interval. Point number two, we have found out an interval dl. Why this is a correct interval? Because distance is constant. At this point, I can say I can find out definite DE. And second thing, if I integrate from here to here, it covers the entire body. So DL is the correct interval. Okay. Now, interesting thing here is, okay, for which I would say we need to understand a little bit. Okay. Now let me magnify that part. Okay. So suppose I have magnified that part DL using a magnifying glass. Okay, I had a magnifying glass. I brought a magnifying glass. Okay, and I have made it magnified. This is theta, right? This is R. This is R. Okay. Now, remember, students, when we okay, why do we say that the total your the circumference of a circle is 2 pi r? Because suppose if you put a compass here and you take a radius r, okay, if you take a radius r and cut it somewhere here, right? So here it will cut. Okay. So this angle, okay, if you find out, right? So which means this is r, this is r. If you do it throughout this circle, okay, you will end up doing it 2 pi times only. So that is how 2 pi times r has become the total, your what you say circumference of a obviously your circle. Okay. Now that is why if this is dl and this is r, so remember students, right? So theta is called as r dl. This into this is equal to this. This is how it is, expressed or in terms of your mathematics. Okay. So we would use this concept in this integration or sorry, in this derivation. That's why I have first explained you this thing. Okay. Now let's go ahead. If you have understood this, the next part is again would be cakewalk. Okay, because next steps are very simple. Okay, yeah. One more step, we should do the vector addition. This is if this is DL, then this would be your DE. If this is DE, and if this angle is theta, this angle is also theta. See, this is important. If you are considering this angle, then which one is theta you need to find out, or else your cos and sine would be opposite, right? They will get substituted. So this is DE. So and this will be your DE cos theta. This is DE sine theta in this scenario, right? DE sine theta. Now, obviously, at a symmetrical place, I will have another interval dl prime, which will also produce a dE, and that can be resolved into dE cos theta and dE sine theta. Obviously, these two vectors will cancel each other, and the resultant would be only this one. Okay. Now the problem is solved. So we have got the interval, we have got the force, and obviously we know which components are cancelling out. The rest is mathematics, right? So your dE will be nothing but 1 by 4 pi epsilon naught. Now charge on this one, right? So I can say q by pi r dl. Okay, kq. Now by r square, what is the distance? The distance is nothing but r only, right? So it will continue to be r. Okay, by r square integration, right? Sorry. Now the interesting part is cos theta. Sorry, in the conventions that we have taken, it will be sine theta. Okay, so it will be sine theta integration, right? And our theta's minimum value would be at this point when my dl is here, which is nothing but 0 degree, and it will be maximum here when it is 180 degree. You can also use 0 and pi convention, whatever you want. So say let us use 0 to pi, okay, 0 to pi sine theta dl by r square. Okay, now r square is a constant that you can take it outside, so I would take 1 by r square also outside. Now here is the problem which I was saying. This is in terms of sine theta, so had this been d theta, it would have been very easy. Now you have two choices: either make it in such a way that you know this thing would be a constant, or express it in terms of dl. Okay, now sine theta, theta is obviously not constant, it's varying from 0 to 1t, so I cannot put directly this one as a constant. What I can do, I can use that formula, right? That theta is nothing but dl into r. So rather than saying sine theta dl, I can say, I can say rather than saying sine theta, I can say sine uh, your r dl, okay, into dl, okay, and then rest is integration. So I will stop it here because this would need a little more complexity. And as I said, we would be going through the concepts. I will model it here and then leave it for you to find out the answer of that. Okay, fair enough. Good. Okay. Or there could be other ways of finding it out also. So if this is theta, then you can draw things like this. And there are different mathematical models that we can use. So I leave you to explore this. If you still didn't find it out, we'll take it up in the next discussion and we will resolve that. Okay. So these are all home tasks for you. Let's move on to the next scenario. Okay. Next scenario. Next scenario, let us go to one more scenario. Okay, scenario 8. So let us try to find out electric field intensity E due to a charged disk on a point P on its axis. Okay, so if you would have seen the diagram in the thumbnail that I sent earlier for this topic, so we had a circular charged disk. Okay, so obviously the difference is now this is a completely suppose, yeah, I that suppose a segment from this board, so that would kind of be a disk, right? And I have suppose given a total charge due to it. Okay, this is the center O, and what I'm saying, at a point P. So suppose from this point I come vertically upward. There is a point P, and I want to find out what is the total electric field intensity due to this entire disk on this point. Okay, that is the scenario. Now let us go step by step. Step number one, can I directly apply Coulomb's law? Obviously not, because the distance of this particle from here, this particle from here, this particle from here, this particle, everything would be different. So I cannot directly apply. Next, obviously the next simple solution is find out an interval which can solve this problem. Okay, so the interval that can actually solve that problem would be this one. And remember students, in physics, once we start visualizing how we can find the interval that can actually solve our problem, the things are half done. Okay, after that it's solving the mathematical problem of integration or everything whatever you have. So say, let me take a distance x, and at this distance x, let me draw a concentric circle. Okay, and from here, let me increase it slightly to dx. Let me draw something like this. Okay. Now, Now I would take this interval as a segment and we would solve the problem. Okay. Now, once you have understood the interval, then we would go to a different view which would help you understand it a little better. First, try to understand this, that why we can take this interval, because if this is the interval, right, and if your x plus dx equals to x, as your dx is very small, right? So which means every particle on this small segment of the disk which looks like a ring, that one is at a distance r from this point. Okay, so what now I will do is I will try to find out charge per unit area, q by pi r square. Okay, now what will be the area of this segment? Simple. So say now if I cut it from here and make it a straight ribbon like this, right? So this one would be 2 pi x, and this is nothing but your dx, right? I repeat, it was like this. Suppose I cut it from here and make it a straight ribbon, right? Then this is 2 pi x and this is x. So what will be the area of this? Obviously 2 pi x dx. Okay, 2 pi x dx. Okay, so after you have understood this, now let us go to solve the rest part of it. Okay, now to solve the rest part of it, so say this was my disk. Okay, from the center of it at a point p, which is at a distance, suppose not r, so say let us say at a distance l, we need to find out. Okay, so we have taken a small segment of width dx whose area is 2 pi x dx. Okay, if area is 2 pi x dx, right, so what will be the total charge on that? Q by pi r square 2 pi r dx. This will be the total charge on that, right? So what will be the small electric field intensity exerted by this? It will be dE. dE would be nothing but 1 by 4 pi epsilon naught into this thing. Okay, now if this is that, if this is your dE, okay, if this is your dE, then yeah, if this is your dE, okay, then obviously your total integration, your total electric field intensity would be integration of this from what was the minimum distance. So minimum distance of x was 0, and the maximum distance would be r, that is nothing but the total radius of the disk, right? So because our interval is x, which is at a distance uh, on the radius from the center. Okay, so we will integrate it accordingly. So x going from 0 to r, integration of this, so this would be your total e net. Okay, so yeah, this would be your answer on it, and rest I would give it as a task to solve, and we would see in the next discussion if you could not find out. And again, students, there could be n number of ways of solving it. As I said, obviously, what is the interval you are doing, and how are you converting. So take again the constants out, solve it, that's it. Okay, now let us go to few more thought provoking situations. Okay, now we are in the last 10 minutes of our this lecture. So I would give you some thought-provoking scenarios. I would help you understand how we can solve it, and then I would appreciate you go home, you do it, and then come back. And remember, students, so I do take my online classes on Saturdays and Sundays at 7 p.m. IST for class 12 students, and for class 11 students at 5 p.m. IST. Okay, and that is only on Saturdays and Sundays, because obviously other days I would not have bandwidth to do that. So if you want to join my online classes, I do have the online class enrollment link on my on the previous video that I had posted as a thumbnail, or you can just ping me or drop me an email, and we can be connected on that. Okay, so in the next 5 to 7 minutes, I would be taking you through few more scenarios which would be more thought provoking for you, and which would be even uh, helping you think in terms of how you can integrate using a small interval to find out the field intensity. Okay, now, so we had taken a scenario, right, initially, that this was a uniform rod, okay, of suppose length L, and we had found out the field intensity at a point on the axis and on the perpendicular bisector. Okay. Now, but in reality, you you may also need to find out, right, the electric field intensity at a distance r from any side of it at a point P, which is not on the perpendicular bisector. Okay, so say if this distance is x, this will obviously be L minus x. Okay, this will be L minus x. Okay, so now let us think how we can find out the total electric field intensity here. Again, as I said I will help you with the step-by-step thinking process here. First one, we know Coulomb's law, I cannot apply directly. Second one, let me try to find out an interval. Okay, so suppose at an interval, now let me start naming this as y, for as x I have already used here. Okay, so at a distance y, I would take an interval dy, and this dy, suppose if this is origin, then on this side, this is if this is your minus x, right? So this total distance on this side, this would be L minus x, right? So within these limits, my interval would vary. Now what I need to do is, on this interval dE, I need to find out, sorry, on this interval dy, I need to find out electric field DE1, or DE1, let's say here. Okay. Now, interesting thing is, as it is not 100% symmetrical, as it is not 100% symmetrical. Okay. So yes. So at a distance, at the same distance y, yes, there would be something that would nullify it's this component. Okay, at a distance y, these two would nullify, but you would have many more points here which would keep giving it your forces in this direction, and they would have component along the vertical axis, and that would not have anything from this side to cancel out, which means in this scenario the problem will be tricky, so that a, for every single interval, we need to find out dE and break it into your I cap and j cap, if I can say I cap and j cap, right? And then only after doing a vector addition and integration, it can be found out. But obviously, as you would have already understood, the mathematical modeling of this one will not be very easy. But that's why I said now we will be going to some thought-provoking scenarios. Scenario one. Okay, let us go to another scenario. Let us go to another scenario. Okay, This scenario, I will make it little easier. Okay, yeah, as I said, right? So one easy, one would be tough, so something like that. Okay, so say this is a rod, okay, and suppose from one end at a distance r from this, there's a point P, and we want to find out the net electric field intensity. Okay, here again the same thing. Your dE will be there. Sorry, so say this is point P. Your dE will be here, okay, and you will have both the components DE. If this angle is theta, this would be your DE cos theta, DE sin theta, right? Right? And obviously, cos theta you should express in terms of nothing but your uh, replace this by your r by r by uh, L square. This is L square plus R squares root over, right? And then you need to find out sin theta also, which would be your, oh sorry, it would not be R, it would, yeah, so if this distance is x, right? So this would be x by L square plus x square root over, okay? And then sin theta would be your x by x by L square plus x square root over. Okay, so after that it will be similar charge per unit length into your this segment dl, and obviously first you need to integrate all the maybe cos thetas, you need to integrate all the your sin thetas, and then only the vector sum will give you the resultant. So obviously this will be complicated, so but then this is the third process. Okay, and remember students, in integration there's a concept called integration by substitution. Okay, so in that scenario, so when you would start solving this one, right? So x by L square plus x square, and then it will be suppose your dx, right? So that would, so here you would have to put, x equals to, a 10u, and then solve it, right? So that is why I'm saying that I would leave it for you guys to understand those things from integration, and then just solve it, and you can get the answer. But from physics and modeling side, this is what is the step-by-step thing that we need to do. Okay. One more last thing for the day before we wind it up. Okay. One more thought-provoking scenario. Okay. So say we have a semicircular ring. Okay. And here we have added two rods also. Okay. Say this is length L, this is length L, and this is a semicircular ring of radius R. Okay, so in this scenario, remember students, if if this is the scenario, then obviously there would, we need to break it into segments. Try to find out for this one in the same way which we did earlier. So DE, if this angle is theta, this will be theta. You will have DE cos theta. This will cancel out. All the DE sin thetas, they would contribute to your electric field intensity. Okay. Similarly, when you find out for these components, okay. So here, suppose you would take an interval. Okay. This is just like your previous problem. At the end of the rod, you are finding it, right? So again, this one would exert some electric field, suppose DE2, okay, and then it will have its own components, okay. Now, if these two are drawn symmetrical, so obviously a similar one on the opposite side from here would also, have a electric field DE and its horizontal and vertical components would be there. Now this component would cancel out this component. Again, it would have DE2 prime in this direction. Now, 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 obviously the resultant intensity would be the total DE1, the total E1 magnitude difference E2 magnitude. Okay, so that is how we can find out. Okay, so I would take a pause here because obviously we have taken a very long discussion. Okay, so as I said, to join my online classes, you can go through my enrollment link that I have on my channel. Okay, I have that enrollment link on different videos, and as I said you earlier also, this would be free for all 11 and 12 standard students. Okay, uh, so and if you want, you can also drop me an email to this mail ID cat rajiv 34 at gmail.com. If you want to be in touch and if you want to join my classes, you can drop me an email on this ID, or if you can go through the Google form that I have in various videos in my channel. Okay, so yeah, but as I said, it's free of cost, and I'm doing it as a community service for students as of now. Yeah. Thank you, students. I hope these things would have helped you understand the concepts of how do we find electric field intensity. But as I said, this is not all. There are many more. So we can take a spherical, maybe a charged sphere, and we can find out electric field intensity. So few we will discuss in the next lecture, and few we would postpone to your Gauss law. So that is how I think it would be the best way we can handle it. Thank you, students. You have a good time. And this is where we end this topic. Thank you, everyone.